So I'm starting off with the same function we talked about in the last lecture, only now you notice I've changed the limit just a little bit. Now, instead of having the limit as x goes to 0, I'm letting x go to infinity. All right, so what I want to do now is I want to think as the x values get really, really big, what does the function do? And if you think back to your college algebra, maybe pre-calc class, this gets talked about there. It gets talked about in the context of horizontal asymptotes, right? And when you do it in those classes, you do it really kind of experimentally. You pick numbers, and you put really big numbers in for x, and you say, okay, look, now I can see the trend, right? Well, now here in calculus we have this shiny new tool. We have this limit, and we can use that limit concept to make this precise. Right, so here we have our official definition, and you notice it's still playing off of these same epsilon ideas, okay? But there's no delta anymore. And I want you to compare this to the definition we had when we were talking about limits that were infinity, where the y values were becoming unbounded. When we wanted to talk about the y value going to infinity, we kind of said, okay, let's set aside epsilon, and we're just going to say y has to be greater than some really big number, b. Okay, we're doing the same thing here. Here, I want to talk about the x values getting really big. So no longer going to talk about deltas, right? I'm going to talk about some number m. What I'm saying is, right, we're following our same pattern, just like always. You pick an epsilon. For any epsilon that you pick, I have to be able to find an m such that every x value greater than that number has a y value that's closer to the limit than epsilon. So if you look at this in the picture, right, you're going to pick an epsilon. It's going to presumably be pretty small here, right? And I have to be able to find some number, possibly way far out on the right-hand side, so that every y value, so that every x value greater than that, greater than m, has a y value that's in here. Okay. Okay, so I want to show that this limit is true. The limit as x approaches infinity of 1 over x equals 0. And this is going to be a really important limit. Practically everything we do for the rest of this section is going to somehow be playing off of this thing. Okay, so I'm going to want to use my definition, right? And my definition says that if I let epsilon be greater than 0, you get to pick the epsilon, I have to be able to find an m such that if x is greater than m, then the absolute value of f of x minus 0 is less than epsilon. Okay, but this is just the absolute value of f of x, right? If I subtract 0, that's the same thing there. And because we're looking at really positive x values, and I know what my function is, it's 1 over x. If I'm putting really big positive numbers in there, I'm always going to get a positive number. So for large values of x, the absolute value of f of x is just f of x. So that's what I need to show. All right, and here's what I'm going to do. I'm going to say let m equal 1 over your epsilon. Right? If that's true, right, then when x is greater than m, that's the same as x is greater than 1 over epsilon. And now I'm going to flip both sides over. This is 1 over x is less than epsilon. Whoa, that's a mess. Less than epsilon. But 1 over x, that's f of x. So f of x is less than epsilon, and that's what I needed to show. Right? That's what I needed to show. So this is 0 is the limit as x approaches infinity of 1 over x. Okay, so let's see how I can use this. Right? Let's take a look at this thing. Remember your limit properties. We're going to use those a lot in this section. All right, this limit is the same as the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 1 over x. Okay, the limit as x approaches infinity of 2 is 2. The limit of a constant is always going to be a constant. And we just showed that this second limit is 0. So this limit is going to be 2. Okay, and I want you to think back to your Precalculus College Algebra class, right? This would be the horizontal asymptote of this function, right? Because this function, if we look at f of x equals 2 minus 1 over x. This is, if we think graphing now, right? If we start with, let's see, f of x equals 1 over x with its horizontal asymptote that we really just saw, right? We confirmed that the horizontal asymptote is here. Well, how do I get to my graph? How do I get to 2 minus 1 over x? Well, first, I do the minus. That's a reflection across the x-axis, so that makes the function look like this, right? And then the 2 shifts it up 2 units, right? So the whole thing, including the asymptote, gets pushed up. And there's my new function. Yeah, you see the horizontal asymptote is at y equals 2. And that's exactly what this limit is telling us. Okay. How about this thing? Well, again, limit properties. This is 5 times the limit as x approaches infinity of 1 over x squared. And that is 5 times the limit as x approaches infinity of 1 over x squared. And now I'm done, right? You see what I said, right? I'm going to keep breaking these things down until they come down to this limit that I already figured out. The limit here is 0, so this is 5 times 0 squared, which is still 0. Okay, so how about this big guy? Now, I want you to remember, right? I want you to remember the rules that you learned for finding horizontal asymptotes back in that college algebra or pre-calc class, right? You learn to do this by comparing the degrees of the exponents. You learn to do this by comparing the degrees of the numerator and denominator. Here, the degree of the numerator is 2. The degree of the denominator is 2. So the method that you learned in your college algebra class was that the horizontal asymptote occurs at 5/3. It's the ratio of these leading coefficients. Okay, well, again, in that previous class, you kind of did it experimentally. Now I can show that this is true, right? Using our new limit. So here's how I'm going to do this. I'm going to divide the numerator and denominator by x squared. I'm going to kind of squeeze it in here, right? Now, when I do this, I'm going to split the fractions up, right? This becomes the limit as x approaches infinity of 5x squared over x squared plus 2x over x squared minus 6 over x squared. So that's all over 3x squared divided by x squared minus 5x over x squared plus 12 over x squared. Now look at how this cleans up. This is the limit as x approaches infinity of 5 minus 2 over x minus 6 over x squared all over 3 minus 5 over x plus 12 over x squared. Now, I'm not going to write out the details any further than this because it starts to get really messy really fast. Where are we going to go from here? We're going to use our limit properties. We're going to take the limit of the numerator divided by the limit of the denominator. And then we're going to take the limit of each of the individual parts. Right? So just so you can see what I'm talking about, I'll write this out for the numerator, and then we'll just put the denominator in from there. So this is the limit x approaches infinity of 5 minus the limit x approaches infinity of 2 over x minus the limit x approaches infinity 6 over x squared. And I do have to write something here, so I'm just going to write the whole thing. The limit x approaches infinity 3 minus 5 over x plus 12 over x squared. So look what happens at the top. The limit as x approaches infinity of 5 is 5. The second limit is 0. The third limit is 0. All that's left in the numerator is 5. What happens in the denominator? Well, the exact same thing. The limit as x approaches infinity of 3 is 3. The limit as x approaches infinity of 5 over x is 0. The limit as x approaches infinity of 12 over x squared is 0. And look at that, we get the exact same thing that you got from your college algebra or pre-calc class. Now, I'm not saying that you should use this method in place of the methods you learned, because it's nice to have just quick rules that we can use in practice. They're called theorems, right? This is a big part of math. It's coming up with theorems to let us do things in a quick and efficient way. So now we've seen why this works, right? Now there's no harm in going back and using those same sets of rules that you learned previously. Right? I do want to take a look at one more, right? Just so we can kind of once again confirm what's happening here. This is a practice. If you want to stop and work through this on your own, you can. Then start it back up and we'll go over it together. Okay, so let's see. I'm going to divide the numerator and denominator by x to the 4th. And the rule here, kind of the pattern here, I'm dividing by x to the biggest exponent in the entire expression, whatever that is. All right, so the numerator becomes the limit x approaches infinity of minus 2x to the 4th over x to the 4th plus 3x to the 3x over x to the 4th minus 2 over x to the 4th. And the denominator is the limit x approaches infinity of x to the 3rd over x to the 4th minus 4x to the 3rd over x to the 3rd minus x over x to the 3rd plus 1 over x to the 3rd. All right, so the numerator, limit x approaches infinity, negative 2 plus 3 over x to the 3rd minus 2 over x to the 4th. And down here in the denominator, limit x approaches infinity, 1 over x minus 4, double checking here. Oh, that's weird. I have 2x to the 3rd. That's why it's coming out strange. Sorry, these x's should all be x to the 4th. Now it's making sense. This is 4 over x. I probably meant for that to be an x squared, but that's okay. It's going to work out either way. Minus 1 over x to the 3rd plus 1 over x to the 4th. All right, now you take the limit of all the individual pieces. The numerator becomes negative 2 plus 0 minus 0 over 0 minus 0 minus 0 plus 0. And now look what I've got here. I've got negative 2 over 0, and we can't do that, right? You can't do that. We can't divide by 0. Okay, so what I'm going to say here is that the limit does not exist, right? The function is unbounded when x gets really large. And this matches what you learned, again, in those previous classes. The degree of the numerator is 4, and the degree of the denominator is 3. The numerator is bigger, and you remember, you learned when the numerator has the bigger degree, then there is no asymptote. And yeah, that's what we're seeing here as well. Okay, let's try another one. This one is a little different. Right now you've got a trig function involved here. And what I'm going to do to solve this one, I'm going to use the squeeze theorem, the sandwich theorem on this one. Let's start with the sine of x over x. Okay, the sine has an upper bound. The sine is never greater than 1. Right? So the maximum value of the numerator is 1. So I know that this is less than or equal to 1 over x. And it's got a lower bound also, right? I know that the sine never gets smaller than -1. So this has a lower bound. This is greater than or equal to -1 over x. Okay, good. Now look at the limits. The limit x approaches infinity of -1 over x is 0. And the limit as x approaches infinity of 1 over x is also 0. And I know that my original function is sandwiched between these two, right? Less than or equal to the limit x approaches infinity sine x over x, which means that that's what my limit is. The limit as x approaches infinity of the sine of x over x is 0. Okay, so now what? These limits, we've just kind of been calculating a lot of limits for their own sake at this point, right? Just to kind of get a lot of practice in. In the next lecture, we're going to see how we can use this concept of a limit to define a whole class of functions, right? We're going to define a class of functions that are called continuous functions. And in a sense, these are functions that are well behaved. They don't have strange behaviors like gaps or breaks or skips, right? It's that class of function that is really going to be our primary focus for the remainder of the class.